All right, let's talk about deep learning. You hear about it everywhere. It's the engine behind so much of the AI that's literally changing our world right now. So today, we're going to pull back the curtain and break down exactly how it works, piece by piece. It all really starts with a pretty basic question. How on earth does a machine learn to see the world like we do? How does it know that's a cat and that's a car, or even understand the words that I'm saying right now? It feels like magic, for sure, but it all comes down to learning from data. So, here's our game plan. We'll start with the big idea of a learning machine. Then we're going to zoom all the way in on its most basic part, the neuron. After that, we'll see how you build a whole artificial brain, how you train it, and then the fun part. We'll watch it see and speak. Okay, let's get right into it. At its core, deep learning is a kind of machine learning. So we've got to start with the absolute basics of how these machines learn anything at all. Well, most of the time, it's done through something called supervised learning, and the idea is actually super simple. Think of it like studying with flashcards. You show the machine an input, say a picture of a cat, and you give it the correct output, the label, cat. You do this thousands, maybe millions of times. A picture is the input, cat is the output. An audio clip is the input, the transcript is the output. At the end of the day, the machine's one and only job is to figure out the mathematical relationship that reliably turns the input into the correct output. So how does it actually learn that relationship? Well, the magic really starts with a single tiny building block inspired by our very own brains, the artificial neuron. Believe it or not, the simplest neural network you can have is just one single neuron. Now, it has a fancy name, logistic regression, but don't worry about that at all. Just know it does one simple thing. It takes in some data, like the pixels from an image, and it makes a simple yes or no guess. Is this a cat or not a cat? It crunches some numbers and then spits out a probability, say an 80% chance it's a cat. That's it. That's our basic decision maker. Right? That's great, but a guess is often wrong, especially when you're just starting out. So here's the billion-dollar question. How does it get better? How does it actually learn from its mistakes? This is where things get really, really cool. Every time our neuron makes a guess, we can calculate how wrong it was. We call this the error. The goal is to make that error as small as possible, to get to the very bottom of that error curve you see on the screen. And the process for doing that is called gradient descent. The best way to think about it is this. Imagine you're standing on a hill in a thick fog. You can't see the bottom, but you can definitely feel which way is downhill. And the way you get down that hill is by following 3 simple steps, again and again and again. First, you figure out which way is the steepest way down from where you're standing. In math, that's called a derivative. Second, you take one small step in that direction. And third, you just repeat. You keep taking these small downhill steps until you can't go down anymore, and boom, you've reached the bottom, the point of minimum error. Your neuron is now as accurate as it can be. Okay, so one neuron is pretty neat, but it's not going to change the world on its own. The real power, the deep in deep learning, happens when we start connecting thousands or millions of these neurons together. Let's see how we build that deep brain. And this is where the deep in deep learning really comes from. Just look at the 2 pictures here. On the left, that's a shallow network. It's got an input, an output, and maybe just one layer in between. Simple. Now look to the right. That's a deep network. The only difference is that it has a whole bunch of layers stacked in the middle. It seems like a tiny change, but adding that depth is what allows the network to learn incredibly complex patterns in the data. And what's so brilliant about this is how it builds understanding, layer by layer. When you show a deep network a face, the very first layer of neurons doesn't see a face at all. It just learns to see super simple things, like basic edges or patches of light and dark. But then the next layer takes those edges as its input and learns to combine them into more complex shapes, like an eye or a nose. The layers after that keep combining those features until finally the last layer can confidently say, yup, that's a face. So we've got the blueprint for our artificial brain, but building it is just step 1. Now comes the really tricky part, training it. And let me tell you, it's a real art form, full of common traps you have to avoid. So here's a classic problem you run into. Imagine a student who just memorizes every single question from old exams. They'll get a perfect score on those specific questions, no problem. But the second you give them a new question they've never seen before, they're totally lost. In AI, we call this overfitting. The model didn't actually learn the subject, it just memorized the answers.
And this slide just perfectly shows that delicate balancing act. On the far left, you've got high bias, or underfitting. See how that line is just too simple? It's completely missing the pattern in the data. Then on the far right, you've got high variance. That's our overfitting problem. That squiggly line is trying way too hard to hit every single dot, even the random noise. The real goal is to find that perfect sweet spot right in the middle, a model that's just right, that captures the real pattern without getting distracted. So how do we hit that sweet spot? Well, we use a bunch of tricks called regularization. And one of the most clever ones is called dropout. Just look at that diagram. During training, you literally just randomly turn off some of the neurons. What this does is it forces the other neurons to learn more robust features because they can never rely on any single neuron to be there. It's kind of like training a team by making different players randomly sit out of practice. Everyone else has to get stronger and more versatile. Okay, we've built the brain, we've trained it to be smart. Now for the really fun part. Let's see what these things can actually do out in the wild. This is the payoff. When it comes to seeing, we pull out a special tool from the toolbox, a convolutional neural network, or CNN. The key idea here is to slide a tiny magnifying glass across the whole image, looking for specific features, like a straight line, a curve, or a patch of green. The network actually learns which features are the most important ones to look for. And with that scanning power, a CNN can do some incredible things, like this, object detection. It's not just saying, this is a street scene. No, it's scanning the image and drawing a precise box around every single car, every person, every sign it finds. It's seeing and locating dozens of objects all at once. This right here, this is the core tech that makes self-driving cars possible. It's also the secret sauce behind face recognition. In this case, the network learns to turn any face into a unique string of numbers. Think of it like a facial fingerprint. Then it can compare the fingerprints from two different photos and tell you exactly how similar they are. That's how your phone unlocks just by looking at you. And it's not all just practical stuff. These networks can get pretty artistic too. This is called neural style transfer. You can take the content from one photo, like your house, and the style of another, like a famous painting, and the network will literally repaint your photo in the style of that artist. It's wild. But what about stuff that isn't a single image? What about sequences, like language or music? For that, we need a different kind of network, a recurrent neural network, or RNN. And its superpower is a kind of memory. The output from one moment in time gets fed back in as an input for the next moment, so it can understand things like context and order. And this is where things get almost science fiction. Because they can process sequences, these networks can start to understand the meaning behind words. They learn to represent each word as a point on a giant map. And on that map, they can actually do a kind of math with meaning. They can learn that the relationship between man and woman is the same as the relationship between king and queen. It's not just memorizing words, it's understanding the abstract concepts behind them. So there you have it. We've built an artificial brain that can see and understand and even create. It learns by finding patterns in the massive amounts of data we feed it. But that brings up a really important question for all of us. As this brain learns from our world, from our text, and from our images, what biases, the ones we have, will it learn too? That's something to think about.